I'm gonna make an exam review video for you for exam 3. Um, this exam is gonna cover everything from intermolecular forces all the way up to anything on up until the end of the semester. So that should be fun for you. Um, since this exam is so close to the final, it's gonna be helpful for you to study this material the most, and then study the previous exams later, since this stuff should be fresher on your mind. The first thing are intermolecular forces. The first thing on this exam are intermolecular forces. So let's go into what those are. So let's first explain what the difference between intra and intermolecular forces are. So an intramolecular force is something that is keeping a molecule together. So actually within inside the molecule. Those things include covalent bonds, ionic bonds, and metallic bonds. So they're part of the same molecule as shown here. Intermolecular forces happen between molecules. So you have two separate molecules here. There's a force keeping them together, and that is an intermolecular force. And these guys are weaker than intramolecular forces, but they do play a very important role in physical properties such as boiling point, surface tension, viscosity, vapor pressure, all that stuff. So let's understand more about what intermolecular forces are. I have the intermolecular forces listed from weakest to strongest, this one being weakest, and this guy down here being strongest. So first, London dispersion forces, they are also referred to as van der Waals forces. You'll see them written either way. Um, all molecules that are somewhat close to each other are going to have this, so keep that in mind. Also, another thing, there can be multiple molecular forces at play. So let's say we have something that is a dipole-dipole interaction. It's also going to exhibit a dipole-induced dipole as well as London dispersion. Hydrogen bonding, same story. Hydrogen bonding is a type of dipole, and we'll talk more about it in the next slides, but it's going to have dipole-dipole, dipole-induced dipole, and London dispersion. However, for this one, keep in mind the ion dipole, it can have hydrogen bonding. It doesn't have to, though. So it could potentially be ion dipole, dipole-dipole, dipole-induced dipole, and London dispersion. So just keep in mind multiple things can be involved in that. So let's go more into detail of what they are. One are London dispersion or van der Waals forces. They are the weakest of the intermolecular forces, and all interacting molecules are going to have these. Here on an example, I have a helium atom. So helium, it's a ideal gas. It's going to have almost no, if any, intermolecular forces, but there can be a tiny, tiny bit. So how to explain London dispersion forces is that there is a orbital of electrons around the nucleus, which hopefully you know that at this point. Um, those electrons are gonna they're gonna jumble around with anywhere within that function. So just by probability, there can be moments where most of the electron density lies on one side. So that is going to give this end a partial negative charge. This end is going to get a partial positive charge because of that. So let's say that we have this molecule now that we just drew on this side. It comes close to another helium molecule. What's going to happen is that positive charge that was now induced from the electrons coming to the opposite side is going to get close to another atom, and that's going to push the electrons over on this end, and it's going to push electrons away from here. So that part's going to be positive. So because of that, those very small, slight charge difference in charges, they are going to be attracted to each other. So that is the basics behind what dispersion forces are. So these are temporary dipoles. They are not permanent. So this happens between nonpolar molecules. And these changes in electron distribution are going to create what are called distortions in that molecule. So things that make a molecule more able to distort are things that make them more polarizable. So polarizability just is how able it is to distort that electron. So if we take larger atoms or molecules, if they're much bigger, they're going to be a lot more polarizable than something that's much smaller. So if we take helium, So let's say its radius is that big. Compared to xenon, xenon is much bigger. So there is it's much more polarizable because those electrons can now go over a different distance, a bigger difference, whereas these guys don't have as much. So a xenon-xenon interaction would be much bigger than a helium-helium interaction. Also, the shape of them, and I'll explain that here in the next slide. So let me move on to the next slide here. So here I just have us do a draw out the intermolecular forces of hydrocarbon chains. Well, I can't speak today. So a hydrocarbon chain is just something that has carbon and hydrogen. So I'm just going to draw it like this. Keep in mind that each one of these peaks is going to have a carbon on it, and then there's going to be enough hydrogens to add to make it equal to 4 bonds. But here, let me erase that. That's confuse us or get in the way. So if we were to draw out a molecular orbital right here, there are going to be electrons just zooming around there. If we take another molecule, oh, and of course I just deleted that. Should have been an art major. Okay, so if you have a buildup of electrons, again, this is all probability. There may be one or two not one or two. There may be a few electrons out there, but if most of them right there are gonna come up there, then you're gonna get electrons are gonna again be repelled by that. Gonna go to the opposite side. And so that's going to create partial, very slight positive charges right here. That's going to attract them. And the bigger this is, so if it's bigger, it's going to be more attracted. One, because it has more surface area, and another because it also is more polarizable, like we talked about on the last slide. So if we compare that to, say, propane, propane's forces are much less. So if we, oh wow, I can't draw. Take propane here, electrons come up there, partial positive, then right there, electrons. Oh, give myself enough space there. Those are going to be attracted, but this one would be much stronger, much stronger. And let's take another example. So shape is going to play a role as well. So let's take pentane and compare it to this guy. What is that? 2-methylpentane. So they have the same number of carbons, same number of hydrogen, exact same molecular weight, but one is going to have a much higher boiling point than the other and much higher molecular interaction. So I'll give you a minute to think about that. Okay, now you had a minute to think about it. Hopefully you pause your video to think about it. The reason that these guys are going to be this one's going to have a much higher boiling point. And the reason is because they can stack nice and easily. And because they stack better, they're going to have more of those interactions. Whereas, let's say we take this, let's try stacking them together. So, okay, we can maybe do that, but then the next one, okay, let's try to stack it. Oh, that kink is kind of getting in the way. If we do another one there, let's try to stack it there. No, so that kink, it's still going to, have some interactions, going to get close to each other, but not nearly to the extent that the other guys do. If you, you can just keep going at it. So this guy is going to be stronger intermolecular forces. There you go. Hope that makes sense to you. Right. Next force we're going to look at is dipole-induced dipole. So a dipole-induced dipole is anything where you take a polar molecule with a nonpolar molecule. A polar molecule has a permanent dipole on it. It has a large electronegativity difference. So you're going to get a large amount of electrons congregating at one side compared to the other. So this side of our water molecule right here is going to have a negative charge on it. If it comes next to an oxygen, which is not polar, it's a nonpolar molecule, if you put it next to each other, that negative charge is going to push the electrons over there, so the electrons are going to kind of reside over there. This is going to make a partial positive charge right here, and that negative and positive are going to attract each other. So this is stronger than the London dispersion forces. And so when we say that there's that distortion, we say that's induced. And because a dipole induced it, we call it a dipole-induced dipole. And then also, sorry, one more thing before I move on. You're going to have to review your polarity rules from last unit so that you can determine whether something is going to exhibit a dipole-induced dipole, because you need to know if something's polar or not. And just remember, look at electronegativity difference and also look at the shape. If something has lone pairs and it's not symmetrical, like say, like water, for example, water has two lone pairs and it's not symmetrical, so that's going to be polar. But if we take, like, say, xenon, and it just happens to have 3 right there, we have fluorine. Those are polar bonds, but because they're pulling in opposite directions, they're going to cancel out. And then also these electrons here, if you can kind of visualize it, that's all happening on the same plane. So that's not going to be polar because it's all of the poles are going to balance each other out. So that's just a quick review for you there. All right, I want to just draw out an example. So acetone with just a normal hydrocarbon chain. So here, if I draw out the orbital of it here, I'm going to draw a big guy right there because it looks like a little, I don't even know what that looks like. Some sort of cartoon thing. So a lot of your electrons are going to revolve around this oxygen here because it thinks it's all important. It's going to hog all those electrons because it is polar. And then if you get it next to this non-polar molecule, again, you're going to get the same thing that happened from our previous example. You're going to get the electrons that are pushed this way. And then that creates a positive charge here. And so just really around this point right here, it's going to create that attraction to it. And this is, again, stronger than your London dispersion forces. All right, the third force is a dipole-dipole interaction. This happens between two polar molecules. So here we have hydrochloric acid. That is a polar bond with another hydrochloric acid, also a polar bond. So you get a permanent dipole, negative and positive are going to attract each other. So that's pretty straightforward. Again, just look for things that are polar. If two things are polar, they're going to have dipole-dipole. If only one of them's polar, other's nonpolar, you're going to go back to dipole-induced dipole. The fourth one is a type of dipole-dipole interaction. It's called hydrogen bonding. Hydrogen bonding is a very strong dipole-dipole interaction. It occurs when you have a hydrogen that is bonded to either a fluorine, oxygen, or a nitrogen. If you do not have a hydrogen bonded to any of these main three guys, you cannot have a hydrogen bond. So here over on the side, we have hydrofluoric acid, H bonded to F. Again, H bonded to F because that the dash line is right here. H bonded to F. So that is your molecule. It can then form a bond with either a lone pair because you have a hydrogen that is bonded to one of those guys. Same thing with water and even this guy right down here. When you're looking at a hydrogen bond, there's two parts. There's the hydrogen bond donor and there's hydrogen bond acceptor. So the hydrogen bond donor is going to be the actual hydrogen that gets exchanged. So in this case right here, our what is that? Butanol, an H that is bonded to an oxygen. It is going to donate the hydrogen part of it to a lone pair of oxygen. So this guy will be your acceptor. And then keep in mind, because that also has an H bonded to O, there could be another hydrogen bond that took place there. Now this guy being a donor, and then there would be another recipient over there. A few examples right here. So acetone right here. If you look right there, there is no hydrogen that is bonded to any of the fluorine, oxygen, or nitrogen. The only hydrogens that are present are bonded to carbon. So if you had just a mixture of acetone, you would not be able to have any hydrogen bonding occur. However, if you had another molecule that did have a hydrogen bonded in one of those, this part of the molecule could act as the donor. So if we have, here, let me draw that better. If we have a water molecule over here, it could potentially act as the acetone could potentially act as a donor to that hydrogen bond. Sorry, it could act as an acceptor to that hydrogen bond donor. And then water. So water is actually capable of donating two bonds at a time and receiving two at a time. So it can technically participate in four at a time. It's mostly not. It's likely not going to participate in exactly four, but it is capable of doing that. And then ammonia, same here. You can have three donors and one acceptor. And then on the next side, I just show them actual configurations right here. So you have acetone. Again, acetone is uh, can't do hydrogen bonds on its own, but from ethanol right here, it can have that hydrogen that would be the donor for it. And then water and ammonia. Look, ammonia capable of participating in four. Here it's not really shown because water, I mean, the way that the geometry works out, it's not going to exactly do four, but you get the idea. Because of the hydrogen bonding and also the fact that water's polar, you're going to get a lot of properties that are very important to life. So ice, if you notice, floats on water. That's because it's much less. It's wow, I can't speak. Because it's less dense than water. The reason it's less dense than water is because when you get it cold enough, these molecules don't move around as much, and so they're able to form this nice hexagonal crystal lattice structure. Not crystal lattice, just a hexagonal crystal structure. Because of that, it then takes up more space than, say, the water right here. So it's going to be much less dense, thus why it floats. Also, because water is polar and has hydrogen bonds, it can dissolve anything that is polar as well. So, like salts, it can dissolve salts because salts are charged. It can dissolve anything that's polar. And then because of these hydrogen bondings, you're also going to get strong intermolecular forces, which take into account the high surface tension of water, also the high boiling point, and a bunch of other factors, and the high specific heat and other stuff like that. The fifth intermolecular force is the strongest one. What it is it's an ion dipole interaction. So an ion dipole happens when you have an ion that's either positively or negatively charged interacting with a polar molecule. So here we have water. I wanted to distinguish that these are partial charges. They are not full-on charges. That's why I wrote partial right there, just to keep that straight. But the partial negative charge on the water from that oxygen is going to be attracted to the positive sodium ion. Then chlorine right there, the positively charged hydrogen portion of the water is going to be attracted to that negative portion. So this one is not an intermolecular force; it's an intramolecular force. I wanted to include it to show you the trend that exists. So if you have two ions, they are going to have a much stronger interaction because you have a total positive charge to a total negative. So in our case here, chlorine's total negative, sodium is total positive. Um, this is the strongest. I think I just said that's the strongest, but also keep in mind that dissolving does happen. So I'll explain real quick because I'm sure some of you are asking questions, either that or you're falling asleep. The reason that it's still able to dissolve here, let me draw it out real quick. I don't want to draw the whole thing out because I'm getting kind of lazy, but if we have water around it, oh, water's not that small compared to it, but whatever. The water, so the negatively charged sides are going to interact with it. Look at how many more interactions occur. So even though that these interactions are less than, they are combined, they still make it more favorable, depending on the salt. If it's a really strong salt, then it probably won't dissolve, but just a moderately charged one is not going to do that. So then same story with chlorine. It's just now instead, you're going to get the negative charge signs. In order to determine the strength of ion, this is from last exam, but I wanted to bring it up because your final's not too far away. So remember Coulomb's law. If you don't, go back and review it before you take the final. This test is not gonna be that important, but you can determine how strong these bonds are gonna be based on Coulomb's law. So yeah, you'll have that to look forward to. So now I gave you some practice problems here, so I'll give you a moment to pause the video to look at those. All right, now that you had a moment to pause it, I just wanted to, I'm not going to go through each one of these individually, but I wanted to give you the tools to do that. And then the answers are on the next slide. So anything that just has um, hydrocarbons or that doesn't have any polar things in it, that's only going to be able to exhibit London dispersion forces if it is with another molecule that, like, say it's with itself, that would only be able to do a London dispersion forces. Whereas, let's say we have this with a polar molecule. So let's say it just had a like that in it. I guess that'd just be three. So that'd be that 1, 2, 3. Then that would be dipole induced dipole because this is a dipole, and then it would induce that dipole in there. So between each of these molecules, also I wanted to give my other. Yep, that's my life. Anyway, so this has a look that has a uh polar right here. Look, there's no hydrogen bonded to any of these nitrogen oxygen. So this is not participating in hydrogen bonding unless there is another, a different molecule that has a hydrogen that's bonded to one of those. This one can do hydrogen bonding because one has a hydrogen bond to that nitrogen, also has an oxygen bound to that hydrogen. This one, fentanyl, same story as cocaine. Um, This one right here, so tyrosine at pH 5.7, that just means that it's going to exist as what's called a Zwitter ion. You'll have to know this for this class, but they're going to have negative and positively charged things. So if it's with itself, it can actually make ion-ion interaction, which is technically not an intermolecular force. We'd actually probably consider an intermolecular force at the, organic chemists would consider that a intermolecular force because it's not covalent, but we're not going to worry about it. They do have a negative and positive charge, so it would be considered ion-ion. Then it could also do hydrogen bonding because of that. And then this guy here, yep, you have one spot for hydrogen bonding here, no other spot. So there are your answers. Keep in mind, again, they could have multiple ones. Also, London dispersion forces are present in all of them. So, yeah, that's fun. Here I got a fun problem for all of you. I know you were just itching for something else, so I the noble person I am, I gave you another thing. Uh this one tells you, so you can look at intermolecular forces or polarity and what different things are to determine how a molecule is going to interact with itself and others. Notice that this is all one molecule. Um, it's going to actually fold over, and so these would actually be considered intermolecular forces, but they're not as strong as the intermolecular force that we think of when we think of like covalent ionic. They're just going to still be the same strength, but because they're more constrained, they're in the same molecule, you're going to have them interact a lot more. I had one professor explain it like if you take two cats and put them in a room, they probably wouldn't interact with each other too much. They'd bounce around. But say you take two cats, take their tail, tie them together. If you take the cats and their tails are tied together, they're probably going to interact a lot more. So that's the same right here because they're part of the same molecule. They're going to interact a lot more. So the cats have their tails tied, and yeah, I could draw a picture of cats out, but I don't want it right now. We can look at so we have a oxygen or hydrogen bond to oxygen. Able to do hydrogen bonds. Here, that ME just means methyl group, so it would probably have been easier for them to write it just like that. Again, another hydrogen oxygen. You can keep going down the line. This one right here is actually sodium sulfate, so that sodium is going to break off, form Na plus, and then this is going to be just a sulfate that's attached to this end. So that's going to be a negative. That's going to be a positive, and that's just going to be a -1. Even though sulfate has a -2, because it's bonded to that, it's going to have a minus. So that would be an ion. It could be potentially ion induced dipole or ion-ion if it's next to another ion. And then yeah, you can just keep going on. I'm not going to go through down all these because I don't want. Yeah, that last slide was really just a trap. So good job. Of the intermolecular forces that you'll need to know. So solubility is just defined as the max amount of something that can dissolve within a solution, and we'll go over that in the next slide. Surface tension is how much energy is required to separate the molecules that exist just at the surface of a liquid. So, like when you do a belly flop on the pool, there's going to be some surface tension at play, and that energy required to break it just went into your belly turning red. Cohesive forces, again, I'll talk more about it in the next few slides. But cohesive forces are forces that keep the same type of molecule together or the same molecule together. Adhesive forces are forces that exist between a molecule and another type of molecule or a different molecule. Capillary reaction is a type of adhesive force that exists in water. The water, like if you look at a tree, you water it at the roots. That water has to eventually make it to the top because the top of the tree needs water just as much as the bottom. But because of capillary action, because those interactions, the tree can bring up the water to the top of itself. And then also, if you dip a paper towel in a glass of water and just hold it there, the water is going to crawl up, and that's because of what's called capillary action. Viscosity is just the resistance to flow. So with higher intermolecular force, you're going to get much higher viscosity. So like for instance, Jello is much more viscous than water, or even like syrup and honey, much more viscous than water because they have much higher intermolecular forces between them. And then volatility just is how much a liquid is able to vaporize itself. So like water, if you leave it out, it's going to vaporize just because there's going to be some molecule. It doesn't even have to get to boiling point. There's still going to be some vapor happening. But if you have the higher your intermolecular forces, the lower your volatility is going to be because it's going to want to hold on to those a lot more. It's not going to want to let them run off. And vapor pressure is related to volatility. And that vapor pressure, the more molecules leave the liquid and become gas, the more vapor pressure is going to exist because you have more. The vapor is going to create higher pressure. Just like the more homework you get, the more pressure you get. So for solubility, like is going to dissolve like, meaning that something that's polar is going to dissolve something that's polar, and something that's nonpolar is going to dissolve something that's nonpolar. A solute is what exists in the smaller proportion, whereas the solvent is going to exist in the larger proportion. So water is your most common solvent, and then a solute could possibly be like sodium chloride or maybe glucose, just something that is dissolved there. So let's get rid of that. So solvation just describes the ability for a solute to surround a solvent to surround a solute. Um, so when looking at these interactions, there's three interactions at play. There's the solute interaction. So in this case right here, this would just be ion ion, and then it could be other interactions as well, but this one would just be ion ion. There is a solvent, so this is what the water is doing before it sees any solute. It's going to just be, bonding with itself, doing hydrogen bonds. Then you get solute solvent. So it happens between your solute and then your solvent. And that would be, if you remember, a little review. Think about that for a second. That would be ion dipole because you got an ion and a dipole. And then again, ion dipole down here. All right, here I pre-drew one of the effects that happen between differences in solubility because I didn't want to have you have to draw it out in front of you and have you laugh at me while I'm doing it because I already have enough to deal with. Just kidding. So these long carbon chains are nonpolar. Water's polar. So let's say that we have water and oil that are mixed together. If they are separated like this is actually unfavorable because if you look, these waters right here are making nice hydrogen bonds that are pretty strong. And they are broken up they're broken up by these big, long, bulky chains. And keep in mind, there are also what is that? Dipole induced dipole. which are they're relatively strong. They're much stronger than London dispersion forces, but it breaks up the networking. Whereas here, let's say we clump all of these guys together. If they're clumped together, now you're given much more area for the water to make those favorable hydrogen bonds. And again, keep in mind that these guys are weaker than the even the dipole induced dipole, but because these guys are so much more favorable to be in that conformation, they're going to exist that way. So that's why oil and water are not going to mix. All right, and the next is surface tension. Um, because water at the surface, or water or any other molecule, is going to be much less stationary because it's not, jumbling around by the forces of the other molecules. It's going to hold on to. It's going to have a higher um, bonding going on. It's going to have stronger bondings that happen. So because of that, when you do your belly flop, it's going to hurt. If you look at your water striders here, they're fun little bugs. So the water strider itself is more dense than the water, so it should sink. But because there is a certain amount of energy that is required to actually break that surface tension, they're allowed to float. So next time you see a water strider, if you take just a tiny little drop of dish soap and drop it in the water, it's going to break the surface tension because detergent's a detergent. And what'll happen is these guys will just sink down to the bottom. So, I mean, I guess you'll be killing a family, but it's kind of cool. Not cool. It is cool. It's yeah. You'll just see them sink if you put a little dish soap in there. So there's a little fun experiment. But if you considered killing things fun, while I'm getting off track, one more example. If you ever been up to the Olympic uh park up in Park City, you have the ski jump that the Olympians practice on in the summer if they don't want to move to Switzerland, or not Switzerland, the southern hemisphere, wherever that is. Uh, Down here, you notice there's bubbles like jets, so they shoot the jets up to break up that surface tension, so that when the skiers come down and crash on the water, it doesn't hurt as bad. Um, so then they also, if you they don't show the whole picture, but they actually have a rock climbing wall on this side that goes up like that I really want to try, and so they'll put the bubbles out there. So if you fall down, like at this point, it doesn't hurt as much because the surface tension is broken up. All right, you have cohesion and adhesion. So cohesion again is going to be within the same type of the same molecule attract to each other. Adhesion is a molecule with another molecule. So here, if water is in a beaker or any liquid, if the cohesive and adhesive forces are equal, it's just going to be nice and straight like that. But if the adhesive forces are greater than your cohesive forces, you're actually going to get it crawling up. So water in glass is going to make this what's called a meniscus, which means in Latin moon. Um, because glass is really hydrophilic, so a water molecule is going to be attracted to that glass much more than they are themselves, so they're going to make that. And then just because of gravity, they're not going to go up forever, but there's going to be a force of gravity pulling it up. On this side, this is when cohesive forces are greater than adhesive forces, and so they're going to make that nice bulge because it's not too much attracted to the end. So good example would be mercury on this side. Mercury is going to be much more attracted to itself than the glass, whereas water, again, you have your adhesive forces that are greater. All right, so volatility and vapor pressure. The stronger the intermolecular forces, the less volatile they are because they're going to want to hold on to these guys. So you got little guys that shoot off and leave, and they want to just be free and not let the man hold them back. But if you have, say you have the oppressive I don't know, the family holding them down, they're not going to leave as much. Whereas this, if they're not as strong, let's say you got a bunch of lazy people right here, they're not, if somebody leaves, they're like, oh, okay, who cares? And yeah, but I hope I didn't lose you in those analogies. All right, next, let's look at phase diagrams. So phase diagrams are pretty straightforward, so we'll go through that pretty quick. You have two main types of phase diagram. You have a normal substance on the left here, and then you have water. Water is just special because if you remember from uh, a few slides ago, ice is less dense than water, so you're going to have that portion of the phase diagram with a negative slope. So let's say, real quick, on each side you have temperature on this axis, pressure on these axes. As you go up, pressure increases. As you go across, temperature increases. So let's say we have ice that is at just a tiny bit below freezing. If we increase the pressure while keeping temperature constant, we could actually turn that into water, not because we're increasing the temperature, which I guess pressure you would increase a little bit, but if we say were to take away any heat added from the pressure, we could still make it water just based on the pressure. So if your phase diagram, take a point in time, you have steam. If you like say lower the temperature but pressure remains the same, it would go to water first, then it would go to ice if you kept lowering it. If you were down here, let's say it was at a low pressure, like way below this would have to be in a vacuum. If you were in a vacuum and the pressure is really low, and then you keep the pressure constant, lower the temperature, it would go go from steam directly to ice. And so yeah, you just follow it for each one. Um, just on the test, look at, are you dealing with water or are you dealing with something other than water? If it's something other than water, it's going to be one of these ones. And then keep in mind, each of these lines is going to be a phase change. Actually, let's go to the next slide. Each of these lines will be a phase change. So here you have melting, there you have freezing, and then down, same thing, vaporization, condensation. Excuse me. There are a few important things to note. Here you have your triple point. So your triple point, all three phases coexist at this given temperature and pressure. At your critical point, you have the threshold for what's called a supercritical fluid. So it's kind of the hybrid between a gas and a liquid. It has the density in between those two things. It diffuses like a gas, or it diffuses through solids like a gas does, but it can dissolve materials like a liquid does. So I know in like dry cleaning and stuff, they'll use this guy. They'll use the supercritical fluids to help clean some stuff. Hey, stoichiometry. This is a fun one. Stoichiometry, you just want to make sure everything on both sides of your equation is balanced. So if you have 6 oxygens on one side, you would have to have 6 oxygens on the other side. And so you would the best method to go about doing it is look at for something that only exists between one thing and another thing on either side of the equation and start with that. So let's go through an example. Here we have carbon dioxide with dinitrogen dioxide goes to that's not even cyanide. What is that? Carbon mononitride. Yeah, and oxygen. First thing I'll do, look, we have carbon only exists on there. Carbon only exists on there. So a 1-to-1. Nice. That's nice and easy. Next, let's look at nitrogen. Nitrogen only exists on here and then there. There has to be 2 nitrogens from this side. So let's put a 2 in front of that. Oh, now our carbons aren't balanced. So let's put a 2 in front of there. So now carbons, nitrogens are balanced. Now we just have to go oxygen. Let's look at how many oxygens we have. We have 4 because we have 2 of these 2 guys right here. So 4 plus 2, that gets 6. So then we'd have to put a 3 in front of there. 3 times 2 is 6. Let's see if we got that correct. Yep, we did. All right. Review your polyatomic ions because it's very possible that he'll have you do a balanced chemical equation by just giving you names. Do an example of that. So it says write out the balanced chemical equation for sodium phosphate reacting with calcium chloride to form sodium chloride and calcium phosphate. You'd have to remember, okay, what is sodium phosphate? So phosphate, PO4, 3 minus. You'd have to have sodium because sodium's only one positive charge. You'd have to have 3. So sodium phosphate would be Na3PO4. Then calcium chloride, again calcium, 2 plus. Chloride has a 1 minus, so you'd have to do CaCl2. And then same story for the rest of those. So let's show the answer of what this would be. That would be what your answer is. So it should be right. If not, then it's wrong. All right, combustion reactions are when you take a fuel and react it with oxygen to form carbon dioxide and water. So let's take an example. Write up chemical equation for the combustion of octane. So let's draw this out. Octane, we get, oh, can't draw it. C8H18, and we're going to say that's solid. That's going to go to, it's going to react with oxygen, which is a gas. And then it's going to form carbon dioxide gas and water. And water is going to actually be in the gas phase too. So let's now balance it. So let's start with the carbons. Carbons are usually easy to start with because you got one on this side, one on this side. We have 8 carbons on this side, so we're going to have to put an 8 here to balance that out. Next, let's look at our hydrogens. Hydrogens, you have 18 on this side, and then 2 for each one, so let's put a 9 in front of there. Now let's just look at how many oxygens we have. So we have 16 from here and 9 from here. Oh, that gives us a negative number. So what I'm going to do is times everything by 2, except this guy, because that's the one we're looking at. So let's put that 2 in front of there. 8 times 2 is going to be 16, so we have 16, be 18. But now we rethink that. That gives us 32 oxygens plus 18. 32 plus 18 is 50. And so then we want to have 50 oxygens, and because there is a 2 on there, we want to put a 25 on there. Here, let me give myself more space. 25, O2, yeah, here we go. So that's how you'd balance that. So to find the limiting reactant of a reaction, you would have to determine what reactant is going to get me the lowest product, because you can only use up as much as the lowest reactant you have. So like, let's say you're making a cake and it requires 3 eggs for every cup of flour. Let's say you had like 3 cups of flour, but only let's go with that. 1, 2, 3, 5 eggs. So if it takes 3 eggs for every cup of flour, you would only be able to actually make 1 unit of whatever cake thing you're doing, because only you'd use up those 3 eggs, and then here, let's just say 3 eggs to keep it simple. Then you would only use up 1 of those, so you'd have 2 cups of flour left over, and yeah, you guys probably get it. You can also determine how much mass is going to be produced based on, you just convert how many moles to the mass. So you should remember how to do that from the first unit. If not, review it. We'll go through some practice problems, so if you don't remember, then you're in luck. So I have a practice problem here for you, so I invite you to pause and try to figure this out on your own before I go through the solution. All right, now that you had a moment to pause, let's go through how we should solve it. So here we have sodium sulfate reacts with lithium chloride to form sodium chloride and lithium sulfate. So lithium sulfate, let's make sure those are balanced out. So we have 2 sodiums from here, so we want to make sure, okay, put a 2 on this side. Then, let's see, is our chloride balanced out? No, so we got to put a 2 in front of here to balance out our chloride. Then let's look, is this balanced out? We have 2 lithiums, which, oh, sorry, that's supposed to be 2 on there. Yes, the lithium's balanced out. Chloride, we have 2 chlorides on both sides, so everything is nice and balanced out. Now we can go to some of our calculations. So let's act as if this guy is a limiting reactant and pretend that we have an excess amount of lithium chloride. Let's see how much sodium chloride will produce. So we have 26 grams of sodium sulfate. We want to convert that to moles. And the molar mass of sodium sulfate is 142.04 grams per mole. So that cancels out. So that's grams or moles of sodium sulfate. Now we want to convert, for every mole of sodium sulfate, how many moles of sodium chloride are produced? So for every mole of sodium, because right here we have a 1 in front of there, basically, so 4, and we have a 2 in front of there, so we know that there's going to be 2 moles of sodium chloride produced. Let's see what that gets us. That gets us, oh, I don't know, I put an extra thing there. We get 0.366 moles of sodium chloride. Now I have to do it out as if this guy's a limiting reactant, and let's see how much it produces. So 43 grams of lithium chloride. Let's convert that to moles. So the molar mass of lithium chloride is 42.394 grams per mole lithium chloride. Now let's convert that to how many grams of sodium chloride are going to be produced. So for every 2 moles of lithium chloride, you're going to get 2 moles of sodium chloride. And a 2 to 2 is going to be a 1 to 1. We didn't have to write it out, but I wrote it out just because so you can understand it, and because it's for fun, kicks and giggles. That gets us, let's see how many moles that get us. That gets us 1.01429 moles of sodium chloride. Looking at this, I know that that has to be my limiting reactant because we have the least amount of this. So now that we know how much sodium chloride is going to be produced, we're going to have 0.366 moles of sodium chloride. And if we wanted to convert that into grams, we could times it by its molar mass. But now we want to know how much excess reactant will be left over. So let's see how we would go about doing that. First, let's determine how many grams of sodium chloride we're going to use up. So we have let me draw a little dashed line so we can separate it. So 0.366 mole of sodium chloride, times that by its molar mass, which is given right up here, so 58.44 grams per mole. That gets us 21.389 grams. And so that's how we do that. Next, we have to determine how much excess reactant is actually used from our non-limiting reactant. So let's first, in order to do that, we have to determine how much of our lithium chloride is actually used up. So let's take our 0.366 mole of our sodium chloride. Let's convert that back into how many moles of lithium chloride. So for every 2 moles of sodium chloride used up, you're going to have 2 moles of lithium chloride. That's going to be 1 to 1. Now we have to determine how many grams of it. So then we have to times that by the molar mass of lithium chloride, which is 42.394 grams per mole. And that gets us 15.516 grams of lithium chloride. I'm going to write used up so that we know what's going down. This is we're not done yet because now we want to know how much is left over. We know how much we're starting with. We're starting with 43 grams of lithium chloride that we're starting with. If we subtract that by 15.516, which is how much we used up, then we are left with, so what does that get us? That gets us 27.5-ish grams. And I'm going to write remaining right there. All right. Hope you were able to do that. If not, or you need extra help, please reach out to one of the TAs, and we'll be more than happy to go through it and talk through it with you. And oh, look, is that right? 28. Yep. If you round it up, it'll get you 28 and 20. Yeah, so we're good. And also, and you will also need to determine, use stoichiometry and gas laws to determine, based on, say, you're given a pressure, temperature, and all that stuff, you would have to then determine how many moles are produced. So keep in mind that at standard temperature and pressure, so standard temperature is going to be 273.15 Kelvin and 1 atmosphere. And this Kelvin is also going to be 0 degrees Celsius. So if you can't remember that exact number, just remember 0 degrees Celsius and then convert it to Kelvin. So at standard temperature and pressure, 1 mole of gas of an ideal gas is going to be 22.4 liters. And so you can determine, okay, how many you can determine how many moles something is given based on liters. So let's do a practice problem for that. Here, I'm going to give you a moment to pause. All right, now that you have a moment to pause, let's go through the answer. To do is first balance the reaction and then use stoichiometry to determine how many moles of NH3 we need. So to do that, we take, okay, we know we have 32 grams of oxygen that are going to react. So convert that to moles, convert the ratio. So then we know, okay, 0.800 moles of ammonia are required. Then you'd have to use the ideal gas equation to then convert that at that specific temperature and at that specific pressure. So then it's just plug and chug at that point, plug your moles in, and that's the answer you should get. And next, we're looking at percent yield and percent composition. So percent yield is basically you take your actual amount that you measured experimentally divided by the expected amount. That's the amount that you would determine from the equations that we used just barely. You can also determine the percent composition of a given substance by, so for instance, say you have something with carbon, oxygen, carbon, hydrogens, and oxygens. If you wanted to know, okay, what percentage of that is carbon, you take, okay, what's the mass of just carbon divided by the total mass of the whole substance. Then you can determine the percent mass by doing that. And this is also known as mass percent. And sometimes you'll have to determine an empirical formula or even a molecular formula based on percent mass and other data that they give you. And we'll go through examples of that here in a second. Here I have a practice problem for you. So I'll give you a moment to pause that and work on that on your own, and then we'll go through it. All right, so first thing that I want to do, let's write up our percent yield again. So percent yield equals your percent yield equals your actual yield divided by your theoretical, so your theo. We know that our percent yield should be 0.64. So let's do 0.64 equals, let's see, what was our did they give us our actual yield? Oh, we want to get 94 grams. So what we're going to do is we are going to act as if that is going to be our actual. So 94 point gram, 94, let's say 94. And we want to know what should we set our theoretical to be at. So it's like we know that we're going to undershoot it, so we want to overshoot it a certain amount so that we can reach it. So if we do that, our x, or here I'll just write theo. Theo is equal, not just Bill Cosby's son in that show, but it equal, let's see, what does it equal? Let's do some math here. 146.375 grams. All right, and that grams of NaCl. So now what we want to do is we want to use our stoichiometry based on this new guy because we want to overshoot it and we know how much we want to overshoot it by. So let's take 146.875 grams of sodium chloride. Let's convert that to our our moles. 4 grams for every mole sodium chloride. And wait, I think I did wrote that wrong. Sorry, that's not the molar mass of sodium. That did look a little big. 58.44 grams. There we go. That would have given us the wrong answer. And then for every 2 moles of, oh, I already got ahead of myself. Oh no, they gave us the equation of here. So for every 2 moles of sodium chloride, we need at least 2 moles of lithium chloride. So 2 moles of lithium chloride. And then we want to then determine how many grams, because it's much easier for us to measure out grams because we have scales. We can't really measure out moles easily. So we have 42.375 394 grams of lithium fluoride per mole. So let's do that out. 46 out earlier divided by okay, so that gets us 106.5 grams. So that's how many grams of lithium chloride we'd have to use in order to get that amount of sodium chloride. I hope that makes sense. Something else you're going to be asked to do on the exam is to determine the empirical formula based on the mass percents that you're given. The method to go about doing this is assume that you're given a 100-gram compound. It just makes the math easier. Then you can convert the grams to moles and then divide by the smallest number of moles from the smallest number of moles from each product. Then you can multiply until you get a whole number. So let's go through a practice problem to show how this is done. All right, so I have a practice problem here for you. So I invite you to pause the video and try that on your own, and then we'll come back and discuss it. All right, so now I had a moment to go through it. Let's see how we'd go through it. First, let's assume that the whole thing is 100 grams because then it makes the percentages nice and easy. So if we had 100 grams, then 2.055% of 100 could be 2.055 grams of hydrogen. We convert that. We want to know how many moles of that would be, so we divide that by 1.008 grams per mole of hydrogen. That gets us a value of 2.039 moles of hydrogen. Now let's do the same thing for our sulfur. So 32.693 grams of sulfur. Let's convert that to moles. 32.065 grams per mole of sulfur. And that gets us 1.0196 moles of sulfur. Now let's do oxygen. 65%, that's going to be 65 point, here, let me draw it lower. 65.251 grams of oxygen. Convert that to moles. Those are all nines, they look like zeros, but moles of oxygen, that gets us 4.0781. So now we divide all of these by the lowest. So this is the lowest number, so let's divide that by 1.0196. Divide that by 1.0196. Divide that by 1.0196. And I didn't label that. Mole of oxygen. This gets us roughly about 2. So 2 mole hydrogen. That gets us roughly 1 mole of sulfur. And that will get us roughly 4 moles of oxygen. Yeah, I can math. And let me write that a little nicer. So now we know, okay, for every mole of hydrogen, we have, sorry, for every mole of our product, we should have 2 moles of hydrogen, 1 mole of sulfur, and 4 moles of oxygen. So I could go, okay, H, we know we got 2 of those. S, we got 1 of those. And then O, we have 4 of those. If you look at that, that's sulfuric acid. So should remember that from last unit, hopefully. So that is our empirical formula. Now let's see what else they want us to do with that. Once you determine an empirical formula, you could then determine a molecular formula if you know what the molar mass of your substance is. So let's go through an example of how to do that. All right, to take a moment to pause and try that on your own. Okay, so from our last problem, we determined that this is our empirical formula. Let's look at what the molar mass of that guy would be. So the molar mass of just H2SO4, if that was our thing, would be 98.07 grams per mole. Now we know that our molar mass, the molecular weight, should be 196.16. So let's take 196.16. Let's divide that by 98.07. That should get us roughly about 2. Almost exactly 2. So now we know that it would have to double, because if we have 2 of 98.07, that kind of sounds like a radio station. But if we have 2 of that, it's going to get us the molecular mass that we need. So let's go from H2SO4 times everything by 2. That's going to be H4S2O8. So that would be our molecular formula. All right, so now let's look at combustion analysis. So we know what a combustion reaction is now. We can actually determine what our molecular formula of, say, a hydrocarbon, or maybe a compound that has carbon, hydrogens, and oxygens, based on how much CO2 is produced and how much. So I have some steps up here for you to follow. Let's use those in an example. So we have 12.915 grams of a substance that we don't know, but we know it contains carbon, hydrogen, and oxygen. Based on the amount of carbon produced and the amount of water produced, determine what the empirical formula would be. So I'll give you a minute to pause that. All right, now that you had a moment to try it, let's go through this fun, guys. Not fungus, but so first let's take. We know that we have 18.95 grams of carbon dioxide. So let's go 18.942 grams of CO2. Let's convert that to moles. And then so for inside carbon dioxide, for every mole of carbon dioxide, you're going to have 1 mole of carbon. So it's going to be a nice 1-to-1 ratio. So 1 mole of carbon dioxide is going to equal 1 mole of carbon. And now we can then determine how much mass, or how many grams of carbon were in that by timesing it by its molar mass. So 12.011 grams of carbon for every mole of carbon. That gets us 5.1694 grams carbon. So now actually, I probably should have written out the equation first. So let's write out our equation. Cx, we don't know that variable, so I'm just going to write out a variable. H, I'm going to say Y, O, Z, reacts with oxygen to form carbon dioxide, and I can't write straight for some reason, and water. So now we know that because carbon only exists on those two, we know that, okay, the amount of carbon produced from that is going to be the amount of carbon that comes from it. We can do the same thing for hydrogens. The water is the only product that has hydrogens in it, and then the only reactant that has hydrogens in it is your compound. So let's do the same thing with water. We have 7.749 grams of water. Convert that to moles, and that's about, what is that? 18.02 grams per mole. And then we want to convert. So for every mole of water, we're going to have 2 moles of hydrogen, because there's that 2 below on the subscript there. 2 mole hydrogen. Then we want to convert that to grams. So 1.0 was that 008? 0.16, that was close. I think. I don't know. 1 mole per gram. That will get us 0.8669 grams of hydrogen. And now the only thing left is oxygen. So how we're going to go about doing this is let's look at what the molar mass or what the mass of this substance is. We know that it's 12.915. So the total mass, the mass of oxygen, not total mass of oxygen is to equal your total mass, which is 12.915 grams minus the combined masses from the carbons and hydrogen. So let's put those in parentheses. We got 5.1694 grams plus 0.8669 grams. And that gets us 6 point. Wait, I did that. Yeah, no, 6.879 grams of oxygen. So now we have to take these values and convert them into moles. So let's do that real quick. So times 12, divided by 12.011, which I guess we just reversed what we did down there, but whatever. And that will get us 0.43039 mole of carbon. And then let's times that by its molar mass, which is, divided by 1.008 for every 1 mole. Put a mole up there too. That gets us 0.8600 mole of hydrogen. And then we take this guy, so 0.42. Oh, wait, what was I? I don't know what I was doing. I had a little mini stroke there. We divide that by the molar mass of oxygen, so 15.999 grams. That gets us 0.4299 mole of oxygen. Now let's divide each of those by the smallest one, which happens to be the moles of oxygen. So let's see what that gets us. This is roughly going to be about 1. Yep. That's going to roughly be 2. And that's going to roughly be 1. So our empirical formula would have CH2O. I hope that you understand that. All right, now thermodynamics is the study of heat and how it flows into and out of systems. If a we'll actually let's go through the slide to go through some of the concepts. So there are 3 main laws of thermodynamics. There's actually 4, but we only expect you to know 3 of them. The first law is that the change in energy of the universe is always going to equal 0 because energy is neither created nor destroyed. It is always present. So if, like, say you have a system and it loses that energy goes somewhere. It just goes to the surroundings and then to the rest of the universe. The second law of thermodynamics states that the entropy of the universe is always increasing. So what entropy is entropy is how it's basically how dispersed energy gets. So it's a measure of disorder. If you have, say, a bunch of particles together, if they move apart like that, that is entropy favored because that energy is dispersed. So if the entropy of a system is greater than 0, or sorry, combined entropy of the universe, so the surroundings and the system, is greater than 0, it is said to be spontaneous. If the change in entropy is less than 0, it is not. So in order for that to occur, that reaction to occur, you'd have to add energy from another source. Um, if the change in entropy of if the change in entropy equals 0, then we say that it's at equilibrium. And then the third law of thermodynamics states that at a perfect crystal, if you can find one anywhere, is the entropy is 0 if it is at absolute 0. So basically, it's just saying there's going to be no movement whatsoever. So there would be no entropy because there's no dispersal of anything. And that is really hard to make. So it's basically saying that there is a baseline, though, at 0 degrees Kelvin and at with a perfect crystal, you would have 0 entropy. So that's where we can actually start measuring our entropy. So that's why the third law is important. So here we have a little schematic, a little diagram of our surroundings and system. So if heat flows into our system, Q is going to be positive. So we're going to have a positive Q value because our system gained energy from somewhere. And that is said to be an endothermic reaction. So let's say this would feel cold because the heat from out here is leaving and now going into the system. Whereas let's say heat now leaves. If heat leaves, the change in entropy, or sorry, the heat would then be negative. So the heat is less than 0. So this process is exothermic. It feels hot because the system is losing that energy. It goes somewhere and it goes to, say, if you're touching it, it goes to your hand. So that's why it feels hot. Now, work is a little tricky, especially for anybody who's taking Physics 105 or 121 right now, because the difference between physics and chemistry is that we define work as opposite things. One of them, well, it really just revolves around, are we talking about is work done on the gas or work done by the gas? So in chemistry, we define things as work done by a system or by the gas. So if work is done on a system, we say that it is positive because it's positive. If work is done by the system, or let's say the system does negative work, that would be negative. So a negative W is going to give you a that tells you that the work is going to be done by the system. So let's say that this thing expands. If that thing expands, the system itself is going to do the work on the surroundings. But because we are putting it in terms of our surroundings, what is done on the system, we have to make it negative because it is doing negative work. It's like, when your mom tells you, I'm not going to go there. Mainly because my brain's not going to come up with something clever. This equation right here tells you the change in energy. It takes into account heat flow and work done. So if heat flows, let's say you have a positive heat, so you gain heat, your internal energy will go up. And then let's say that work is done on your system, so it's compressed. That would also be positive. So that would be really positive. If, say, your gas or the thing expands, the volume increases, then we say negative work has been done. This could be negative depending how negative this guy is. And then let's say that it's an exothermic process, it's going to let go of some of that heat. And then if work remains constant, say work is 0, then your change in energy is going to be negative because now your system lost energy, so it's going to go down. I hope that makes sense. If not, again, reach out to any of us and we'll go through it. And then, yeah, I realize that there's more slides. So the left side of the slide, endothermic process, and on the right side of the slide, you have exothermic processes. All right, so how do reactions feel? When they go to therapists, what happens? Exothermic reactions are going to feel warm because they are taking the heat, or sorry, they're releasing the heat from the system into you. So the Q is going to be negative because it's getting rid of that heat. An endothermic is going to feel cold because it takes that heat away from the surroundings and brings it in. So that is going to make Q positive because now the internal energy of that thing just rose up. So we can measure the heat based on these guys. So we have a C value, and we'll talk about each of these specific ones, times change in temperature. So heat capacity is defined as how much energy is required to raise an object 1 degree Celsius. So the most common place you'll see this is if you're looking at a calorimeter. So calorimeter is fixed. It's always going to stay the same calorimeter. It doesn't magically transform into another one. So because of that, each calorimeter has a specific constant with it, a specific heat capacity constant. You plug that in and you see how much does that calorimeter change. Does it move up by 10 degrees? Does it move down by X amount of degrees? You can then determine that by that right there. So the change in temperature would be your final minus your initial. So here we'll write that in there. So specific heat capacity is more useful when you're dealing with things like water or maybe a skillet or I don't know, your roommate if you want to heat him up, or maybe your mutual date. Okay, I'm not gonna go there. So specific heat is how much energy is required to heat up 1 gram of a substance by 1 degree Celsius. So we're actually given a mass, and the important thing to note is the units. So our units of our constant are going to be in joules per gram degree Celsius. So if we have, say, X amount of grams, times it by our heat, which are specific heat, grams would cancel out. So if you're unsure which one to use, just look at your units, and your units should cancel out and leave you with just joules if you are solving for Q. And then molar heat capacity, same thing. It's just now you're dealing with moles, so your N would have to be moles. Look at your units. If your units are in moles, then use the molar heat capacity. If you, let's say you're given only a mole, a molar heat capacity, and you know how many grams, you would have to convert from grams to moles. So here are the formulas that you need to know. Again, this is the one we went over a few slides ago. So you have heat and work that play a role in your in the change of internal energy. Now this guy, we're going to go through this in more depth in the next few slides, but here we can measure the heat required to, in this case, how much it takes to either melt something or to freeze something. Given them a certain amount of moles and the constant, we have to know the enthalpy of fusion. We can times in the number of moles times that, and that's how much energy is required to freeze it. And then let's say that says that instead. If that was vaporization, we would that's how much energy is required to convert that many moles to a gas, or vice versa if you're going in the other direction. This is how much energy is required to heat up a substance a certain amount, and we went over in the last slide, so I'm not going to go over it again. Work, you can calculate work out by taking the negative pressure times the change in volume. So if we think about this conceptually, if the volume goes from big guy to little guy, so our final minus our initial, that's going to give us a negative number. So a negative times a negative is going to get us a positive value. So we say positive work is done. And if we think about it, yes, work has been done on the gas or on the system. If, let's say, the other way around happens, we have a little guy goes to a big guy, the volume expanded because we go final minus initial, so big guy minus little guy, still going to be positive value. So positive times a negative is going to get you a negative, so that's going to be a negative one. And then this bottom guy right here, this is enthalpy. Enthalpy is related to internal energy, but it also takes into account your P times your change in volume. So it takes into account both those things. If your P change in volume doesn't change, then your internal energy actually equals your enthalpy. So yeah, at a constant, here, that's what this bottom one is. At a constant pressure, delta each H, so your enthalpy, your change in enthalpy equals your heat. And then here, pay attention to your units. One more thing, you need to have this guy memorized. This is the specific heat of what, that should be specific heat. Specific heat. Here we go. The specific heat of water is 4.184 joules per gram degree Celsius. If you don't remember this on test, just remember also 1 calorie is also the specific heat if this was in units of calories. So 1 calorie per gram degree Celsius equals 4.184 joules per gram degrees Celsius. So just remember that one. That's a nice easy number to remember. Then look at your conversion sheet on your equation sheet and convert calorie to joules, which 1 calorie equals 4.184 joules. So that's how we get that number if you happen to forget it. So here, during a phase change, if you look as we add energy into it, look at what's happening to the temperature of the system. It's rising up until it gets to a certain point. So this guy is the melting point. The temperature doesn't actually change while it's melting because all of that energy that is being put in is going into breaking those intermolecular forces. Once we break all those intermolecular forces, so in this case, once it's all melted, then any more heat we add would actually heat up the temperature. Then once we get to the top right here again, once it's vaporizing, it requires a certain amount of energy. So if we were to determine, actually, let's go to the next slide and talk about that. All right, so if you are changing from one state, if you're heating up something, say you're at this point and you're going from here, the equation that you would use would be this guy. The equation from our last slide equals N delta T HVAP. So those were the equations we went over earlier. Let's say that we started at this point and we want to know how much energy is required to get it to that point. So one, we have to use this equation right here to determine how much energy is required to heat up that amount of substance to the boiling point, which if it's water, it'd be 100 degrees Celsius. Then we would have to use this equation to determine how much energy is required to actually, once it's at 100 degrees Celsius, how much energy is required to now vaporize all of that. So at this point now, everything's vaporized. Then we want to heat up that water vapor even more. So we'd have to do that equation and add it up. So then we would take the values that we get from each of these equations, add them all together, and that would get us our answer. That is how much energy is required to go from this point to that point. So I hope that makes sense. We'll go through a practice problem here in a minute. And okay, yeah, so the negative Q of your substance should set it equal to water. I probably should have explained this before running off. When you drop something in the water, you can measure how much. You can determine how much the water temperature changes, or you can determine how much heat was in there. There's a lot of things you can do. What you do is you set one of them negative, one of them positive. The Q transferred is going to equal because that heat has to go somewhere. So I would set the Q, the water, since it's gaining that heat, it's going to be a positive Q. Since whatever you're dropping in there, if it's hot, it's going to be negative Q. And then if it's the reverse, if say you're dropping a cold thing in there, it'd be positive, but that would be reversed. Then you could set those equations equal to that guy. So MC delta T, you'd be given the specific heat of that. Or if you weren't given, you'd be given all the other variables to solve it. And then you should know the specific heat of water. And then you could just set that equal. And then again, that is final temperature minus initial. So you can use that most often to determine the final temperature of the water. And my timer is going off, so I think it's time for me to go to Thanksgiving dinner. And I'll get back to this in a second. All right, guys, I'm back. So let's talk about calorimetry now. Calorimetry is a way to measure how much heat is produced. So here, if we give out our things here, this styrofoam cup represents a white trash version of a calorimeter. So what a calorimeter does is it is basically a thermos that isolates the heat or isolates the surroundings so that there's no heat that escapes. Any heat that is measured or a change in heat that's measured or that's absorbed will be directly measured somewhat, but it's pretty accurate, so it's pretty good depiction. So this would be your thermometer in there, and it would just measure the change in heat that happens during a reaction. So you can either burn something, or in this case right here, if it's done in a styrofoam cup, it's probably going to be salt dissolving, and you can measure how much heat is either released by the absorbing of the salt or absorbed, depending on what type of salt it is. So yeah, you would just do the same thing that we did before. You just take the mass of the water, or if you're doing the calorimeter, you would actually have a constant with that calorimeter. But if you're measuring the change in the water, you'd have to take the mass of the water. It just depends what units they give you. And yeah, so you would if they didn't give you the specific heat of the calorimeter, you'd have to do the Q of the water, and you do that with MC delta T. All right, and then just do the same thing that we were given earlier. I said earlier, calorimetry can be used to measure dissolved salt. I really just put the slide because I wanted to show this fun little picture right there, a salt and battery. Look at how cute they are together. All right, guys, I got a practice problem here for you. So give this video a pause and try that on your own. Okay, so how you go about doing that is you get your Q equals MC delta T. It absorbed 290 kilojoules of energy. We need to convert that into joules. Let's set that equal to the mass of our water. That needs to be in grams. So we're going to do that many grams, times that by the specific heat of water, which is 4.184 joules per gram degree Celsius. And then we want our change in temperature, so that's going to be our T final. Let's see how high up it gets us. Subtracted from our initial temperature, which is 30 degrees Celsius. And so if we solve that out, our final temperature equals, let's see, what does it equal? It equals 82 degrees Celsius. So is that enough? No, because we have to get it up to 93 degrees. So no, it's not enough. But you are enough. Remember that. Always remember that. Problem. So you know the drill. Pause it. Give it a try. I know you will because you're honest, good people. Okay, now we will try it. So first, let's set up our expression. So the Q of our water needs to equal the negative Q of our skillet. That's because the water is going to gain that heat, whereas the skillet is going to lose that heat. And we need to set that negative so the heat is being transferred. So let's see how much heat the water would gain from that change in temperature. So if it goes from 25 degrees Celsius to 100 degrees Celsius. So let's first, so this equation, first we're going to have to use MC delta T to determine that heat. So, but also, one, we're heating it from 25 degrees to 100 degrees Celsius, but we also want to convert all of that into steam. So once it's at 100 degrees Celsius, then we're going to have to add whatever our fusion enthalpy is. So then we're going to do plus number of moles times the enthalpy of fusion. Sorry, not fusion, vaporization. That is going to equal negative Q of the skillet. So let's do that real quick. So we have 10 grams of water. Let's times that by our specific heat, which is 4.184. We love that number. Feel like Bob Ross talking here. Happy little numbers. We go. Wait, did I do that right? Yeah, no, we're good. We have 101 degrees Celsius as our final, subtracted by 25 degree Celsius. We'll give him a little friend because everybody needs a little friend. So that is how much energy is required to heat up the water that much. So let's put the whole thing in brackets there. Now we need to add up from the VAP here. So the enthalpy of vaporization is, let's see, what is that? It is 40,800 and, wait, no, 670. So if we do, we have to, and notice that is in, I didn't give you units here, sorry. Units are going to be joules per mole, just joules per mole, because we're not actually dealing with a change in temperature because it has to be at that 100 degrees Celsius. So let's take 10 grams. We need to convert that to moles. So that would, you'd have to divide that by the molar mass of water, which is 18.02 grams, 1 mole. Then let's times that by our number up there, so 40. And notice how much bigger that number is. It takes much more energy to actually vaporize something than it does to heat it up. And so then we set that whole thing equal to the negative Q of the skillet. So we put a negative in front of it. And then the specific heat of iron, I probably should have given that to you. I can spell, all right? Specific heat of iron equals, let's see, what does it equal? 25.19 joules per mole degrees Celsius. So we're gonna have to do another conversion because we're given grams. So we have 120 kilograms. That's gonna be 1,200 grams. So 1,200 grams. Divide that by the molar mass of iron, which is 845 grams per mole. And then I'm running out of room here, so I'm gonna just how do I do this? Just draw that arrow there. There we go. Times and then we want to go from moles to how much energy is actually produced. So we times that by our 25.19 joules divided by mole degrees Celsius. Then we have to do our change in temperature. And then if we were to solve that out all algebraically, I'm just going to show the answer real quick. It gets you, let's see, I'll write it up here. No, I'll write it down here. So your change in temperature is going to equal negative 47.5 degrees Celsius. So that's telling us that we are getting colder. So it's an endothermic process, and it's 47.5 because that energy is now going into the skillet. Well, the energy is leaving the skillet and going into the water. All right, we got yet another practice problem. I want to give you so much fun opportunity. So yeah, take another minute to pause that. All right, so let's try that. We have Q equals MC delta T. If we look right here, they give us 39 liters of water. So something that you should probably know for future reference is that the density of water is 1 gram per milliliter. So if I were to convert that to milliliters, I would do 39,000 milliliters of water. That is going to equal 39,000 grams of water. So now I can take, okay, Q equals, is that what we're solving for? Assume, no, okay, so, okay, oh, no, never mind, sorry. So yeah, Q, let's see how much heat is released when we burn that amount. So you have that much. We're using water again, so it's going to be, that's going to be grams. So we have 4.184 joules per gram degrees Celsius. And we're raising the temperature by 58. So we don't even have to do the final minus initial. We just plug that in as it is. So 58.0 degrees Celsius. Then Celsius cancel out, grams cancel out. We're left with joules. And that gets us a number of 9.46 times 10 to the 6 joules And so now what we can do is we need to determine how much, for real quick, for every mole of this that's burned. Oh wow, I don't know what that little bump is. For every mole of that burned, we're gonna get that much energy. So let's determine how many moles, or actually grams is what it's asking for, how much we'd have to burn in order to get this amount of energy. So let's start with that energy. We got 9.46 times 10 to the 6 joules. Let's do our conversion. So for every mole burned, so mole, what is that? C2H6. It's going to release, that needs to be in joules, so let's convert that real quick. 3H2000 joules. And then after we get to moles, we want to go to grams. So let's times that by the molar mass, which is 30.070 grams divided by 1 mole of C2H6. That will give us 744 grams of C2H6 that we need. So let's now look at Hess's law. So each reaction is going to have a standard enthalpy change with it. And most of the times you're going to be given a reaction that has a not known enthalpy change. So you can determine what the enthalpy change is by looking at, by combining multiple reactions together. So for instance, we have the combustion of methane here with the breakdown of carbon dioxide. So if you put those two together, oxygens cancel out. On this side, you'd have to double that because if you see you have half an oxygen. Oh no, sorry. Yeah, no. So half of that's going to cancel out. So you're left with 3/2, which is what we're looking for. And then the carbon dioxides cancel out. We're left with carbon monoxide and two H2Os. And so we don't have to modify that at all. We just add those numbers together. So the negative 890 plus the 283 is going to be negative 603. So let's do a practice problem now. Un momento to solve this, s'il vous plaît. All right, now let's go into it. So we want to rearrange all these guys down here so that it looks like this guy. So I wanted to give you something that is a little challenging, so it'll stretch you a little bit. First thing that I'm going to do, let's look at what we need to get in order to get our main guys. Let's first look at where our P4010, and this isn't written very good, it's not in subscript, but I don't really care right now. So if you look right here, that is on the opposite side. So we're going to have to flip it. If we flip something, we have to reverse whatever the sign is. So let's write that out. We have P for O10, sorry, not O11, O10 plus, or sorry, it goes to, let's see, what does it go to? P4 plus 5 oxygens. And let's write out what that change in enthalpy would be. So we have to times that by negative because we flipped it. So negative times negative is going to be a positive. That's going to get us 2967.3. So not kilojoules. Now let's look at how we can get this guy on there. So let's look at where PCl5 is. So that is right there. Okay, and it's also good. We're also going to have to reverse that. So that's nice and fun. And also, look, there's a 6 there. We're going to have to times that by 6. So we're going to have to times the whole thing by negative 6. Let's write that out. So let's put a 6 in front of it. So 6 PCl5. And that is going to 6 PCl3 and 6 Cl2. And so we take our other thing, we times that by -6. And let's see, what was it? It was -84.2. So that's going to get us 505.2. All right, now let's do, we need to get that guy. We haven't accounted for that guy yet. Oh, look, okay, we don't have to reverse it, but we need to times everything by 10. So let's do that real quick. So that's going to be 10 PCl3 plus 10 times a half is going to be 5. So 502 is going to translate into 10 Cl3PO. And so then we're going to take, here, I'm too lazy, I'm not going to keep writing that out. We have 10 times your -285.7 equals, see, what does it equal? -2,857. So now we have all of our players. Let's look and see what we have so far. So our, what do we have? So these 2 oxygens are going to cancel out, or the 5 oxygens here, and the 5, because we're looking at this side here. So that's going to cancel out, and this right here is going to cancel out 4 of them. So we still have 4 remaining. We're going to have to cancel that out with another thing. So let's look at the last equation that we haven't used yet. That one. We still have to get P4, one of those getting rid of, and we have a fourth of that. So let's just times it by 4 and see what it does. So we times 1/4 by 4, it gets you P4 plus 3/2 times 4 is going to get you 6. So 6 Cl2 grams is going to move to 6 PCl3 grams. Here, let me get rid of this thing. Now let's see what we can do. Okay, so now we have those that cancel out. Oh, wait, oops, I don't know, I put a 6 there. That should be a 4. Got a little word there for a second. So the 4 right there, that cancels out the rest of that 4 right there, so we can get rid of that. Now let's look, Cl2. Yep, those cancel out. P4 cancels out. Let's check to make sure everything's left. So if I had more room, I'd write it out. But you have P4O10 plus 6 PCl5. Yep, that's what we got up here so far. Nothing else on this side goes to 10 Cl3PO. And I forgot to put this one out. So let's times that by 4. So 4 times -306.4. That is going to equal -1225.6 kilojoules. So if we add all of these up, so I'm just going to draw a little thing here. That gets us an overall value of negative, here, I'll just, negative 6,000, or sorry, negative 610.1 kilojoules. So pretty good. The standard change in enthalpy is actually looking what's called the standard enthalpies of formation. So each element has a standard enthalpy of formation, which will be given to you on the test. Except keep in mind that any pure element is going to have a delta H, so a change in enthalpy of formation of 0. So example would be oxygen, nitrogen, any noble gas, any pure metal. All of those delta formations are going to be 0. Another rule of thumb, though, is if we don't give you a enthalpy of formation of a certain substance, just assume that it's 0 and you'll be right. So what we can do is we can take the sum, so add up all of the sums of the product of the enthalpies of formation, subtract it by the total sum of the enthalpies of formation for the reactants, and that gets you the overall change in that reaction. So let's give it a go. Let's try a practice. All right, let's try this practice problem. Give yourself a few minutes for that. All right, so how you go about doing that is first, let's write up our equation there. We got your delta H naught going to equal the sum of your products of your your enthalpies of formation minus the total sum of your reactants and their enthalpies of formation. So let's do that real quick. We have delta H naught equals, let's look at what our reactants are, or what we actually first have to write our equation. I'm getting ahead of myself. So the equation for that, and this is practice from earlier, I'm just going to write it out. We have ethanol plus O2 goes to form CO2, H2O. Let's balance that out real quick. You have 2 on that side, 6, so we put a 3 there. And we have then a 3, and let's see if that's balanced. Yep, so that should be nice and balanced. Now let's look at what our products are. So, those guys are our products. And these guys are the reactants. So let's take this one. So we have 2 of our carbon dioxide, so 2 moles, because we're asking per mole of reaction. So for every mole of reaction, there's going to be 2 moles of that used up. So for 2 moles of CO2, we times that by the enthalpy of formation, which is that guy. So -3. Here, I'm going to put that all in big brackets. 393.5 kilojoules per mole. And then we add that to our other one, which is water. So we put a 3 in front of it. So 3 moles of water. Our waters is going to be -285.8 kilojoules per mole. And those are all of our products. So now we need to do our reaction. So we have to put a minus there. And let's put another big bracket here. Let's look at what our ethanol is. So ethanol, we just put a 1 in front of it. So 1 mole times -277.7 kilojoules per mole. Add that to our oxygen, which is 3 mole times, and then oxygen, remember that is a pure element. So that's going to be times 0. So that makes it nice and easy. And then just another rule of thumb, we didn't give it to you, just assume it's 0. And so if we calculate that all out, that gets us a nice value of -1, 3, 6, 7. Here, I'll write it over here so we can. -1, 3, 6, 7 kilojoules. So that is your bake right there. At the enthalpy of a reaction, or to determine the enthalpy of a reaction, is to look at the bonds that are broken and subtract them from the bonds that are formed. Notice that it is reversed because bonds broken are going to be your reactants. Bonds formed are going to be your products. So you don't get mixed up, I want to teach you a concept. When bonds are broken, so let's say we have carbon and carbon. If a bond is broken, that is going to require energy. So that's always going to be positive. When a bond is formed, it's going to release energy. When a bond is formed, if it releases energy, that should give you a negative change in enthalpy. So just look at anything that's on the right side of a reaction. You're going to have bonds formed. So add all those together. Or sorry, subtract them because you're going to have a negative change in enthalpy. So anything on the right side, make that negative. But anything on the positive side, because it's requiring that much energy, you're going to have to put energy into it, hence why it's positive. So let's give ourselves a practice problem over here. A minute to solve this problem. All right, now that you've had a minute, let's look at what we're going to have to do. So we are going to have to, one, break this bond. So if we look up here in our table, we have end to end. It's going to be 163. We're also going to break that bond, break that bond, break that bond, break that bond. And we are going to form one of these bonds, so a triple bond. We look at, that's up there. And we're going to break two of these because there's a 2 in front of that. So I have our answer on the next slide. So this will be our answer because we are breaking 4 of these nitrogen-hydrogen bonds up here, 1 of the nitrogen-nitrogen bonds, and then we're breaking 1 of the triple nitrogen bonds. So that's why we have a negative in front of there, because we're forming the bond, so it's going to release energy. And then 2 of these, so we have a 2 in front of it. Again, we're forming the bond, so it has to be negative. And then these guys are positive because we are breaking those bonds. So I hope that makes sense. Keep in mind that this process isn't 100% right, because let's say that that's bonded to a nitrogen instead. That might affect that bond. But for our purposes, we're going to say that it works out nice and easy for us. I have a quick example for you. It's pretty much the same thing, so give yourself time to solve that. Answer for that. So first, you would have to write out the combustion equation. So again, applying what we learned before. 2 of those, balance that out. It reacts with oxygen to form carbon dioxide and water. And these are what the guys look like. So we have a double bond there, double bond, double bond. So those are going to be different energies. And then you add them all up. Remember, anytime you break a bond, that's going to be a positive. Anytime a bond is formed, so anything on the right, you're going to have negative for that. And so your overall value is going to be negative 2,831 kilojoules. All right, so the fuel value of something determines how valuable a fuel is. Can't argue with that logic. So anything that's going to give you the most change in enthalpy per gram. So if they ask you a question to determine what has the best fuel value, just determine what gives you the most energy per mass. And that should be pretty straightforward to solve. Now, entropy. We touched on this a little bit earlier, but let's go a little bit more in depth into it. So entropy is the technical definition is it's the increase of the total number of microstates, which means that the probability of these guys moving around is going to be much higher. So as you start off with your nice ordered structure right here, over time, all of that energy is going to dissipate, and so you're going to get some scattering of stuff going on. Another way to think about it is, say you are making a campfire. If you make a campfire, initially that all that energy is concentrated right on that fire, and it feels really warm. But if you keep the fire going and you don't pour water on anything, you just let the natural course run, eventually it's going to burn out. And because, according to the first law of thermodynamics, that energy is not destroyed. There's not energy going anywhere, but that energy is now dissipating outwards, and it's going out all the way into outer space. And because that energy is going out, we say that the entropy is increasing. The actual change in energy did not change of the whole universe, but that entropy scattered out. So that's why it feels much colder, because that heat, instead of being concentrated in that fire, is now spread out all the way across. So the things that are going to increase entropy is larger size, also lower rigidity. So if something is nice and loosey goosey, it's going to be a lot harder to keep it in line as something, say, that's really rigid. Like let's say we have a diamond right there. Diamonds are pretty rigid, so they're not going to move around as much. The entropy is going to be very low. And that's also why, according to the third law of thermodynamics, a perfect crystal at 0 degrees Kelvin is going to have no entropy, because those perfect crystalline structures are the most rigid, and they're going to have the lowest entropy. Also, more moving particles, more entropy, should make sense. Greater volume, you have greater entropy because you have more space for the molecules to move around. And then greater temperature, also you're going to increase you're going to increase entropy because your kinetic energy is higher. You're going to have stuff moving around a lot more. The S naught is your absolute entropy of 1 mole of a substance at standard temperature pressure. So at your 273.15 and at 1 atm. So calculating the change in S naught kind of sounds like snot. You follow the same rule as you do with your enthalpies, but now you take number of moles, the sum of your product minus the sum of the enthalpy. Make sure you have your moles in front of it of the reactants of the entropies. And so I'm not going to go through a practice problem of those because it's the same thing that you did for the enthalpy. If you feel like you need extra practice, please go to the problem set or the smart work. I would actually recommend doing that anyway, but since my time's limited, let's just not go do practice problem right now. And then here's just another review slide from something we talked about earlier. So the first law of thermodynamics is that the change in energy of the universe is zero. So energy is not going to be created or destroyed. And so energy can only be converted from one form or transferred. And the ways that it's transferred, you have your change in entropy, or sorry, energy. Well, the is equal to the Q plus the W. And we talked about that earlier, so I'm not going to go too much into it. But I do want to talk about this. The change in energy of your system is going to equal the change in energy of your surroundings. And because the universe right there is going to be equal 0, if we add this plus this, that's going to equal, so if instead we write it delta E system plus delta E, so I add it to both sides, delta E of surroundings equals the delta E of the universe, which equals 0. So that's how that derivation is found. Because any energy that is lost from a system has to go somewhere. It's going to go to the surroundings. If it is, in this case, that is a endothermic process. If that was negative, then that would be an exothermic process. And yeah. The second law of thermodynamics states that the entropy of the universe is always increasing. So like that fire example that we have, here, let's draw it out just for, wow, we're going to say that's a good fire, right? Draw a little log. If you comment that my log is good, I'll give you extra credit. Okay. So as the entropy spreads out, the fire is eventually going to burn out. When the fire burns out, we'll draw an arrow right here. We'll draw sad logs. And they're actually mostly just kind of black. So if I could draw a black set right there, we'll just say that's it. So now we just have the burnt out flame. That energy still exists. It's just spread out. So more spread out. Because of entropy. And yep, I forgot that I had that equation there. Luckily, it didn't go too much into my fire. And oh, look, that's what I wrote earlier. So that's right. Okay, so I have just a quick conceptual question. So a particular reaction is spontaneous and has a change in entropy of negative 163 joules per Kelvin. So what must be true about the entropy of the surroundings? So take a moment to think about it. The according to the second law of thermodynamics, the change in entropy of the universe, so we'll put a little universe there, universe, must be greater than 0. We know that we have to have it at least positive 163, if not more, because we need to add that plus that needs to be greater than 0. All right, so here for a reversible process that occurs at a constant temperature, we say that's isothermal. So we can actually determine what your entropy would be if your temperature doesn't change given your Q value. So we would have to first calculate our Q, divide that by our temperature that doesn't change. That'll get us our change in entropy. So this is an important equation that you'll need to know. Let's apply that to, oh wait, there's more stuff. So a reversal process is one that can recur in both directions. So let's say we have A plus B goes to C. It would also happen in reverse. So we draw the double arrows because the C could then go back to A and B. It's just going to go happen at fourth. And when the rate of A and the rate of C, the rate of the forward reaction reaches is the same as the rate of our reverse reaction, we say that it is in equilibrium. So if we were looking at it in a beaker, we wouldn't see any change. But in reality, there is forward reaction going and reverse, but they're just happening at the same rate, so we don't see an overall change. And all systems are going to reach equilibrium at some point if they're allowed to run to that point. So yep, then we have our same variables right there. Equation gives a good estimate for delta S so that we can determine the entropy for phase changes and then also for the surroundings. And all right, guys, got a practice problem for you. Real quick, one more thing I forgot to say in the previous slide is that when you plug it into your equation, your temperature needs to be in Kelvin. So I'll give you a minute to solve that, and then we'll go through it together. Okay, so if you remember the equation, here, I'll write it up here. Your change in entropy is going to equal your Q divided by your change in temperature. We have to determine Q. We're not given Q. So remember, Q equals, in this case, this is we say it's freezing. So if you remember, freezing is an exothermic process because it's losing energy to the surroundings. So because it's exothermic, we have to put a negative in front of it. So all exothermic processes have negative. If it was endothermic, then it would just be positive. So that would be negative N for moles times your enthalpy of fusion, which is given to us here. So now let's plug that in down here. We have Q equals 50 grams. So we have to convert that into moles. So 1 mole of mercury is 200.6 grams. And then now we can times that by our fusion, enthalpy of fusion, which is 2.29 kilojoules. Now keep in mind, this is in kilojoules. We have to convert it to joules because we want it in joules. Because the units of entropy are joules per Kelvin. So to do that, let's do that. We have 2290 joules per mole. So then moles cancel out, grams cancel out, and that gets us an overall negative 571 joules. Sweet. Now we can plug that into our delta S equation. We have negative 571 joules divided by, and then we have to do it in Kelvin. So let's convert to Kelvin. So we have 38.9 plus 273.15. So if we do all that math out, it gets us negative 244. Oh, let me write that a little nicer. Negative 2.44 joules per Kelvin. So that's actually that's a pretty good entropy. The fact that it's a negative entropy tells you that it's becoming more ordered. And if we think about what's going on during freezing process, we have first, if it's in a liquid form, it's scattered. If it goes towards solid, so 1, 2, 3, 4, 5, that is going to be more ordered. So more ordered. Entropy decreased. But yeah, think about conceptually what's going on. If, like, say the other way around was happening, if we went from a solid to a liquid, which is melting, your entropy would be increasing because now you have particles that are more scattered. Now let's talk about Gibbs free energy, or just Gibbs energy. A lot of people just think the free there. Um, so what Gibbs free energy is, it just tells you how spontaneous your reaction is going to occur. So how much energy is actually available to do free work. And so this equation right here, it relates your delta H with your delta entropy at a given temperature. So let's think about this for a minute. Let's say we had an endothermic process. So your delta H would be negative. If you had a positive entropy, your delta S would be positive. Now, real quick, let's take a little break and go down here. If your delta G is less than 0, that is a spontaneous reaction. So a negative delta G is spontaneous. If your delta G is a positive value, if it's greater than 0, it is non-spontaneous, or another way of putting it is the reverse reaction is spontaneous. So in order for the reaction to occur, you have to add energy from another source, which that's when you get to coupling and stuff in biological systems. You have to have energy from another source. If your delta G equals 0, then your system is at equilibrium. It's not going to flow in either way, or it's not going to favor one flow over the other. So going back to this, let's say our delta H was negative and our delta S was positive. So negative minus, notice there's a minus, we take positive times that right there. So this could potentially be spontaneous if, actually no, sorry, this is always going to be spontaneous because a negative minus that positive right there, you're always going to get a negative. So if your entropy is increasing and it's an exothermic process, it's always going to be spontaneous. If, on the other hand, let's say we had a positive change in entropy, sorry, in enthalpy, so it's an endothermic process, and let's say our entropy was decreasing, that is not spontaneous. And we'll go through this more in detail on the next slide. But if we, like, say we had an exothermic reaction and a negative entropy, that could potentially occur with a negative that could be spontaneous if your temperature is low enough. Because if you notice, you have a negative. If you subtract that by another negative, you're going to be adding it. But if that temperature is low enough, it's going to bring this whole value down. And so you would have to have it at low temperatures in order for that to be spontaneous. Whereas the other way around, let's say it's an endothermic process. Wait, did I already use that one? Did I? Yeah, let's say it's an exothermic process. And no, I did use that one. Wow, okay. Well, let's say it was an endothermic process and the change in entropy is negative. So endothermic reactions are not that favorable, but if the entropy is high and then at high temperatures, the higher your temperature, the higher this value can be. So at high temperatures, relatively high temperatures, you're going to get a negative G because now you get a minus, a plus is big enough, and that will be spontaneous. So hopefully that equation makes sense. If not, try some practice problems from the problem sets or come talk to a TA. Let's go through it in the next slide. So here's just a chart showing you, like, okay, you have a negative change in enthalpy, so an exothermic process with a positive entropy, so it's becoming more disordered. That's going to be always spontaneous. And you could just memorize all these and you'll be fine, but I think it's much easier to look at the equation. That way you don't have to spend extra time memorizing stuff like that. So just understand how the equation works. If you can understand how the equation works, then you don't have to memorize this. So again, just as a reminder, a positive entropy means that it's becoming more disordered, and that is favorable. If it is a negative entropy, it's becoming more ordered, and that is less favorable. You'd have to put energy in to do that. Whereas A negative enthalpy is going to be exothermic, and that is favorable. That would be a spontaneous, that would help in spontaneity. If it was positive, then that was endothermic. You have to put energy into it, and so it would go against spontaneity. All right, here again, calculating your delta G value. If you are given your delta H, you're given the temperature, and you're given the delta S, you could just plug those numbers in and find the delta G. And if you're, this could also be a multi-step problem. Say you don't know delta H, you could use it, you could find it on any of the other methods we did a couple slides back. If you didn't know delta S, you could do that also by doing the methods described in a couple slides back, and then times it by whatever your temperature. And this temperature is in Kelvin, so make sure that temperature is in Kelvin. And then you plug those in, that'll give you your delta G value. Okay, so now we are going to calculate your delta G based on your standard Gibbs free energy of formation. So kind of the same thing with the standard enthalpies of formation. I'm not going to go through any more practice problems with that because it is the same concept behind the enthalpies of formation and the entropy of formation. So last little slide just mentions how these Gibbs free energy things are important. So in biological systems, a lot of time, well, not a lot of times, all the time, when we want to get energy out, we have to put some energy in. You know, there's probably some deep gospel analogy you can draw to that. But for instance, in your uh, the Krebs cycle, Krebs cycle, the citric acid cycle, you have to put in some energy before you get the energy out. But because we do what's called coupling, we can combine some reactions that are unfavorable. So if we have like a delta G that has a positive value, we could combine that with a delta G that has a negative value. And if that negative value is big enough, I'll write two negatives to make it super big, it would overcome the unfavorability of that non-spontaneous reaction. So in order for a non-spontaneous reaction to occur, you'd have to add energy from an outside source, usually another reaction. And that is the basics behind biological stuff. That's really all you need to know. You'll probably need to know a lot more in your biochemistry class when you get there. It'll be so much fun for you. And so that is my whole review. Again, if you had any questions on any of the material discussed, please reach out to me or any of the other TAs. Also reach out to Dr. Asplund. Um, the number one thing you can do to do well on these tests is actually practice the problems yourself. So go through the the problem sets, go through the smart works, and make sure you can do them without checking the answers first, and then check your answers and make sure you did them right, and then you can do it. Then also look at the practice exams that Dr. Asplund spends out, and then there's also a study guide posted that just lists the bullet points of or each of the concepts that'll be covered. I wouldn't use that as like the only thing you study, that study guide. I would just use that to make sure if there's like something on there that you haven't seen before, you don't know what that means, to go and ask questions about it, go and find some problems about that. So that's going to be the best way to go about studying for the exam. So yeah, you guys will do great. This exam also, I forgot to mention, all multiple choice. So there's no free response section. That is a good and bad thing. It's a good thing in the fact that you can always check your answers. Check the possible answers, like doing stoichiometry. You can look and see which that rather than go through all the options, you can look and see, okay, these are the four options. But it's also bad news because if you mess up on a calculation, you can't get partial points. It's all or nothing. So, but you guys will do great. Again, reach out to me or any other TAs that got questions, and we'd be more than happy to help. Thank you, and good luck.